Start with a quick show of hands. How many of you today are using Amazon EKS? Okay, good deal, good deal. Another quick show of hands. How many of you are using Apache Spark today? Okay, also a good deal. Seems like a little bit less. And then last question, how many of you are running Apache Spark on Amazon EKS today? Okay, well, awesome. Thank you so much for that. And with that, we are going to get started. My name is Alex Lyons. I'm a senior container specialist here at AWS working on EKS. I'm joined by my colleague Vara, as well as Som from Pinterest, and I'll let them introduce themselves a bit more when they take over. So today, I'm going to talk about Kubernetes for data processing, and then use that as a segue into what we've built at AWS that we call our Data on EKS project. I'm then going to hand over to Vara, who's going to talk briefly about open source data platforms on EKS, and then Som is going to share with us the modernization journey that he's been a part of with Pinterest as it relates to their data processing. And then finally, Vara is going to come back and talk about some best practices for running Apache Spark at scale. So, Kubernetes for data. What do financial simulations, autonomous vehicles, genomics research, and machine learning recommendation engines have in common? Well, for one, they're all powered by data. Data is a key input to each of these processes being able to deliver the value it is that they deliver. It's what makes them go. Another thing is that all of these are running on Kubernetes today, and specifically on Amazon EKS. Whether it be Bridgewater, building the financial simulations that help them understand global financial markets, or Mobileye, building the autonomous vehicle technology that's in an estimated 150 million vehicles worldwide, or companies like Roche Pharma doing biomedical research, or companies like Pinterest building machine learning recommendation engines. All of these run not only on Kubernetes, but on Amazon EKS today, and they do that at a massive scale. But why Kubernetes for data? Well, we see 4 key reasons for this. And the first is scalability. Kubernetes allows you to independently scale the compute and memory for your application so that your infrastructure can meet your application's needs. It has capabilities like the horizontal pod autoscaler and cluster autoscaler, and there's a number of open source tools like AWS's open source Carpenter that can help you manage this autoscaling so that your infrastructure can meet the needs of your application. Another key reason is orchestration. When it comes to data workloads, the Kubernetes orchestration can manage things like automating your job resubmission when a job fails. You can also specify the CPU and memory resources at the job level so that you can have a very fine-grained control over the resources that you're allocating to your applications. Another key reason is portability. So if you are running on Kubernetes, that means you're running containers. And with a container, your application code is packaged alongside all of the dependencies that it needs to run, like environment variables and libraries. Because of that, you'll see less things like job failures when promoting from one environment to the next, because all of those environment variables are going to be packaged alongside that code, so you can have a faster time to market or time to production for these applications. Another thing that this portability gives you is the ability to run multi-version clusters. So you can actually run multiple versions of Spark or other frameworks next to each other in the same cluster, whereas if you were on a VM-based architecture, you would have to either spin up a separate VM, which is going to incur additional costs, to run those other Spark versions, or upgrade all of the versions, all the jobs to the next version of Spark, which is going to be a very cumbersome process. So that portability gives you some flexibility there as well. The last key reason is standardization. Now at AWS, we see a number of customers adopting Kubernetes at scale. And they typically do this by what we call standardizing on Kubernetes. It means that they're making it their default compute option for orchestrating their containerized applications. What this looks like in practice is typically by building a Kubernetes platform that's managed by a central group, and it provides developers with the things that they need to get to production. CI/CD, observability, governance, generally abstracting away those infrastructure details from the developers. Now, when a customer starts to see the benefits from this, like a faster time to market, like decreased costs, they want to extend these benefits to other applications. They also can then leverage the investments that they've made in both people in terms of the central group, as well as the tools that they've built, and they can leverage those investments further. So that's another reason why we see the growth in adoption of Kubernetes for data workloads. Now at AWS, in working with customers to help them build these data workloads on EKS, we have noticed a common set of challenges that customers run into. These are very compute-intensive workloads, and many have very volatile scaling patterns. If you think about batch processing, and sometimes they need to scale up to over 1,000 nodes and back down and do so relatively quickly. Your clusters need to be configured to be able to support that. Another thing is building a highly available application. These are stateful applications, and your disaster recovery is going to have to account for that. It's going to need to look different. It's also setting up observability for what could be thousands of nodes and potentially millions of microservices. Alongside all these, there were a number of decisions that we were helping customers make around the right network configurations, compute and storage options, and also batch scheduling options so that they could build workloads that were ready to scale on EKS. And in helping them solve these problems, that is why we decided to build and launch our Data on EKS project. So Data on EKS is a collection of what we call blueprints to help customers build modern data platforms on Amazon EKS. Now with the project, we release these blueprints, and a blueprint includes a reference architecture so that you can visualize what it is we're helping you deploy in your environment. It also has infrastructure as code, or IAC templates, that help you actually spin up the AWS resources and also install the open source tools and any necessary prerequisites to actually run these applications in your environment. And this is done following AWS best practices. So those best practices are built right into the IAC templates. And then finally, we give you sample code to test. In the instance of Spark, we give what are known as TPC-DS benchmarks. It's a very widely used benchmarking framework so that you can not only install these resources and tools in your cluster, but then also have sample code to test it against whatever solution you have today to make sure that it does meet your requirements. So Data on EKS is a public open source project. We publish all of these blueprints to our website, which you can see a screenshot of here. And our goal is really to share this knowledge as broadly as possible with the community, recognizing that Kubernetes is open source and there's a vibrant open source community around not only Kubernetes, but also data tools and how the two are evolving together. And we want to continue to support that. We build blueprints for the use cases that we see as the most prevalent amongst our customers so that we can be as beneficial as possible and add as much value as possible. Now, primarily that has been around machine learning. This could be end-to-end, from training to serving to machine learning operations as well as data processing, primarily with Spark, which is what we're here to talk about today. And with that, I'm going to hand over to Vara, who's going to talk a little bit about open source data platforms on EKS.
Thank you, Alex. Hi, everyone. My name is Vara Buntu. I'm a principal solutions architect working mainly with open source technologies, and I specialize in data analytics and Kubernetes. So one of the key things that I wanted to show you today is how you can actually run open source data platform on Kubernetes. As you can see in this slide, this is the various stages of the data platform within the Kubernetes, starting with the data ingestion. And Kafka is most popular to run like in the streaming workloads for the data ingestion. But I would like to bring your attention specific to the data processing related to this talk. So within the data processing, we have a number of tools like Spark, Flink, Pandas, Dask, and Beam. And all these tools are used to do the data processing, which is both batch processing as well as stream processing. However, a lot of our customers, majority of the customers, favor towards Apache Spark for both batch processing and some for stream processing as well. Now, let's get to a little bit of introduction about Apache Spark. Apache Spark, and I guess most of you said that you are using Apache Spark. Apache Spark is a distributed processing engine, which is mainly used to process terabytes and even petabytes of data across distributed with multiple instances. It comes with a set of libraries like Spark SQL, MLlib, streaming, and graphics, which is mainly used to process various types of data. You can run Spark on your standalone machine, such as your Mac or Windows machine, whatever, but mainly to write your scripts and to process small set of data. However, if you want to process terabytes and petabytes of data, you need to use a resource manager such as Yawn or Mesos. But in 2018, Spark community added a support to Kubernetes as a resource manager, which means you can run your Spark jobs on Kubernetes in a distributed manner, and Kubernetes acts as a resource manager. Now, let me show you the end-to-end how Spark on Kubernetes works. As you see on the slide, and we have control plane and the data plane. When user submits a Spark submit to a control plane, and the scheduler will schedule the pod, and with the Spark core and a headless service, which is Spark driver gets created in the data plane. So as a step 2, driver requests API server for a number of executors to be created. And the scheduler will create those executors in the data plane, and these executor gets connected to driver pod using that headless service that you see. That's how the end-to-end communication for Spark on Kubernetes works. But now I'm going to hand over to Som Acharya, who's going to talk about Pinterest modernization journey. Thank you.
Hi, folks. First, thank you, Alex. Thank you, Vara, for giving us an opportunity to talk about what we've been doing with EKS and our modernization journey thus far. First, a couple of words on what Pinterest is and what it does. It's a visual search and discovery engine with some social media flavorings. I think Wall Street sometimes considers us as social media, but I think we don't necessarily feel that we're more in the visual search and discovery side of things. At the last quarterly report, our monthly average users, or MAUs, were at 482 million. And our motto is people use Pinterest to find inspiration for creating a life they love. We work in the metaphor of pins and boards. So you find assets, you find websites, pictures you like, you pin them, and you organize these pins via boards. So that's a kind of a top-level summary of what Pinterest does. In terms of how that actually translates into data processing, here is a highly kind of opinionated overview of what the data flow within our infrastructure looks like. So users are manipulating pins and boards, and they're doing so via apps and via the web browser. And then there is also a source of third-party data as well that can be, for instance, merchant catalogs and things like that. So those flow into our front-end API services. And then downstream from the front-end API services, we have large Kafka clusters for getting log information in a streaming real-time way. And that can go into our streaming infrastructure. Or, for instance, there are databases that, say, keep track of users' board and pin memberships, for example. And so there are data services that take care of that, and then dumps from those databases and output of Apache Kafka also flows into our massive kind of S3 data lake. And then downstream of that, we have our big data platform, where a lot of batch and streaming processing occurs. And then in conjunction with the machine learning platforms that are also running there, we output signals, we output models, recommendations, and a huge set of data warehouses. So that's kind of a highly opinionated view of really kind of data flowing and being processed to produce kind of useful data products within Pinterest. Zooming in further on our batch processing platform, so currently we are using Hadoop, or at least we're using Hadoop in a fairly massive way. Some quick numbers, Hadoop cluster nodes at this time, around 14,000 EC2 instances plus in the cloud. Our biggest cluster is around 2,500 plus nodes. We run about 70,000 Hadoop jobs per day. We process hundreds of petabytes of data daily, and we have more than half an exabyte of data in S3 under management. So with that in mind, we have a very big Hadoop base. Why would we consider moving to Spark? There were a couple of reasons for us. Hadoop is an established service, but we felt it was getting old. We wanted to move to something a bit more cloud native, more agile, and there was already a lot of momentum towards Spark internally at Pinterest. We had been moving our Hive jobs to Spark SQL, for example. We had been moving a bunch of our MapReduce jobs to Spark to take advantage of, I think I'm preaching to the converted here, a lot of the benefits that Spark offers. We've been investing in kind of Spark upgrades and modifications to the central Spark code base. So that part was a no-brainer. And then moving on to a cloud-native solution like Kubernetes, like EKS, that would allow us to really try things to drive kind of greater cost efficiency opportunities. That was very tempting, and then all taken together really reduced the dev iterative cycle, right, and improves productivity. So those really were our main reasons for moving. Our Spark on EKS platform, we call that Mocha. So this is a complicated diagram. I don't have much time to spend on it, but bear with me. One of the reasons I wanted to throw this up is to point out that just getting Spark on EKS by itself is not sufficient. You have to build a bunch of supporting services around it if you really want to process data at scale. So on here, starting from the left-hand side, is kind of how users interact with the system. So we have a notion of, you see a system service called Spinner. That's our Airflow-based job DAG writing or composing tool. So that really produces workflows. And then we have a service called Archer. And what Archer does is it's a job submission service that we wrote specifically for submitting jobs from taking these DAG definitions from Spinner and submitting them into a set of EKS clusters. And then within EKS itself, we have multiple EKS clusters that run. We had to outfit those with the Spark operator that Vara and Alex have been talking about or will talk about more. And then for scheduling, we are using Unicorn, right? Because we found that Unicorn, for us at least, was the closest analog to Yarn on Hadoop. And then beyond that, when jobs run, they will need images to pull from, and that's where ECR comes in. And even though we have gotten rid of Hive and are running Spark SQL, we still need the Hive metastore because that's where the table definitions are, okay? And then you notice we have some of these other boxes that are in slightly different colors. These are services that we're working towards that will provide things like Jupyter and kind of Spark SQL UI submission, and then also finer grain access control and more security. On the top right-hand side, there is also the remote shuffle service. So as you guys know, Spark itself has an external shuffle service, but we felt the need to move that to a separate service to open up possibilities like auto-scaling within the EKS cluster. So that's an ongoing piece that's an ongoing project that we are continuing to invest in. And then once jobs run, they produce metrics, they produce logging, so there are services to consume those. Users will want to connect to the live Spark UI once the job is running. So we have an ingestion service that allows for that. Sorry, an ingress service, rather. And then once jobs have finished running, they'll want to see logs, and that's where the Spark history server comes in. A quick note on the migration timeline. So last year, we spent evaluating a variety of Spark runtime solutions before settling on EKS. In H1 of this year, we kind of hunkered down and started productizing and selecting EKS and Spark on EKS settings. So we focused on how to operationalize, putting in logging and metrics, and then really shifting our first set of jobs away from Hadoop into Mocha. So that's around 10%. And then this half, we are now starting to kind of come up on the edge, looking at some of these scaling opportunities, and looking to migrate around 20% more jobs. In H1, we migrated Spark Scala jobs exclusively. This half, we are focusing on a mixture of Scala as well as Spark SQL and migrating those. Next year, our focus will be doing more work with integrating into the rest of Pinterest. Specifically, for instance, the Pinterest service mesh is a big one. We want to look into PySpark migration as well, finer grain access control, and then start open sourcing some of these components that we have, because we feel that there would be a need in the community. I'm sure we are solving problems that others will also encounter. So if you guys are interested in learning more about some of these, happy to share. So in summary, some of the wins and learns we have had from our projects thus far. A big win for us was being able to move to Graviton and a bunch of cost savings that comes from moving to that. Thus far, our Hadoop clusters had been running on Intel AMD-based instances, but now our EKS clusters are Graviton. And then getting access to standard Kubernetes APIs at a deep level means that we can kind of mix and match various open source components, right, and get them running without fear of necessarily running into compatibility issues and things like that. We don't have to worry about managing the control plane for the Kubernetes cluster. That's taken care of. And then open source components that actually have an AWS flavoring, like OTel and FluentBit, that's been very useful for us as well, simply because we've been able to work with AWS and really get an understanding of how best to deploy that within the Pinterest environment. Pricing is always great, meaning that the EKS overhead is minimal. Most of the cost actually comes from the EC2 instances. We're always looking for opportunities to save, so this was icing on the cake. And then, as we mentioned throughout the talk, the data on EKS and EKS blueprints are things that we have leveraged into our Terraform deployment infrastructure to make it easier to deploy clusters. And then, of course, underlying, the support and work with the various AWS folks here has been tremendous, and we're hoping to do more of that going forward. In terms of the actual sizing, we have a couple of clusters totaling around, I want to say around 800 nodes, actually. So it's, and then we want to get to around about 1K by end of year, and next year we have even more ambitious plans in terms of cluster sizing. Some of the learns for us has been, deploying EKS comes with its own set of challenges in terms specifically networking and load on EC2 APIs. So we have had to work carefully with the AWS team to kind of get around some of those things. Control plane logs, like to find a better way of exporting those into the Pinterest infrastructure. So that's one thing. And then, because we have run our own Hadoop cluster, forever and ever, we are kind of accustomed to mixing and matching various Hadoop patches and deploying those into the platform. So obviously, because we don't own EKS, we don't have that luxury. We have to, adhere to the EKS kind of Kubernetes release schedule. The regular EKS upgrades, that's another thing. The fact that you're essentially on the clock and you have some time, but you still have to migrate EKS versions. So that's also a consideration. On the Spark side, I could probably talk a fair amount on just that alone, but I'll keep it brief. One of our goals for migration was we wanted to keep all the details hidden or transparent to the user. So from our internal customer standpoint, they're simply writing Airflow DAGs, and they don't care where it goes to. whether it goes to Hadoop or whether it goes to Mocha, that should be immaterial. So what that meant is we had to be careful in terms of capturing job configurations and making sure those got translated into the Spark on EKS environment. And then note that because we're changing instance types and architectures from AMD to Graviton, native libraries, we have to be careful and make sure we can migrate those to Graviton as well. A big one is because we're shifting away from Hadoop, Hadoop actually, in addition to running MapReduce and Spark, provides a bunch of other things that we kind of take it for granted, right? So provides the yarn scheduler, it provides log aggregation, it exports metrics, it has its own file system, it has a UI, right? And so in moving to this, we had to find alternatives or write some custom stuff from scratch. So that's another consideration going forward. And then because of the scale at which we operate, some of these alternatives that we found, right, they're kind of rough around the edges and means that we have to do that much work into them to make sure that they operate at this, at the scales that we are accustomed to. So overall, I think, and I don't use this term lightly, I would say that moving to EKS is something that is transformative for kind of Pinterest data engineering, and also I would say for infrastructure. So in terms of going forward, we have been heartened by our success with Spark on EKS, and we're looking to do the same for Flink, which is what we use for our streaming platform, as well as TiDB, which we're using more on the storage and caching and the key value store side. And then eventually, we'll have other workloads also move to EKS. So thank you for listening, and I'll hand you back to Var.
Thank you, Sam. Right, thank you, Sam. Right, so many of you said you are running Spark on EKS. One thing I wanted to ask you, how many of you hit IP exhaustion issue when you are running Spark at scale? Like some, I can't see with the light, but. Right, so we're going to discuss some of the best practices which helps you to scale your Spark workloads on EKS. So you can avoid some of the common issues by following these best practices. And then the workloads vary based on customer to customer, how you run. And we will help you at AWS to solve some of those problems to scale your workloads to the desired state that you are looking for. So in this slide that you see, it's a VPC CNI with secondary CIDR. One thing we noticed that a lot of customers with the data teams and data science teams, they just go out and ask platform team that create an EKS cluster so that we can run Spark jobs. And the platform team have no idea how many IPs that they need to allocate. They just normally create a smaller subnets, and then the data team hits that issue saying, hey, we can't run the jobs anymore because we ran out of IPs. So that's a common issue. We highly recommend customers, like a few, to consider the networking configuration. And the configuration is something that I'm showing on the slide where you can use a private, like within the VPC, you can use 2 routable subnets. Those are mainly with a small CIDR range. Those are mainly used for load balancers or any public interface or talking to your on-prem data center and so on. But when it comes to running your actual Spark workloads, even the nodes, you can leverage the secondary CIDR range with non-routable IPs. As you see here, I have 2 subnets across 2 AZs, and each private subnet on the secondary CIDR range has got 65,000 IPs, which means it can give you 120K plus IPs or the Spark pods that you can run on Kubernetes. Now, the other thing that we tend to see from the customers when they are running at a scale is unknown host exception from CoreDNS. This is a very common thing. There's one thing that you can avoid this issue is using horizontal scaling for CoreDNS with a cluster proportional autoscaler. So what normally happens when you deploy your CoreDNS, by default, it comes with the 2 pods for your EKS cluster. But when it comes to running thousands of nodes, those 2 pods are not enough to distribute or provide the service to the rest of the the pods. So to avoid the situation with this cluster proportional autoscaler, you can actually horizontally scale co-DNS pods based on the size of the worker nodes that you are spinning up. And another best practice is using node local DNS caching, which means you can build the caching with a simple kubectl command to deploy the node local DNS caching on every single node that allows you to improve the performance rather than going back to the core DNS to get the DNS resolution. Now, moving on to the storage. Storage is really crucial when it comes to running Spark on Kubernetes. You might be running the workloads before on Hadoop or any other Hadoop-based flavors like EMR. But running Spark on EKS, storage is completely a different ballgame. Like as you see in this slide, when you want a high performance and a low throughput, we highly recommend using NVMe SSD-based instances with Spark. As you see on the slide, you have 2 worker nodes, and one worker node is C5DX large, another one is C5D12X large. And C5DX large has 1 NVMe SSD attached, which is 100 GB. For C5D12X large, has 2 NVMe SSD attached. But when it comes to using these volumes as your shuffle data for Spark jobs, you can use Spark local directory to point to that specific storage. You can use host path. In this case, as you see on the slide, there is a volume that defines the host path. But the case where you have multiple SSDs within the EC2 instance, how does data engineer know whether the instance has 2 disks or 1 disk? To avoid that situation, we recommend using RAID 0 config, as you see on the worker node 2. Look, when you spin up these nodes, and you can configure RAID 0, which will give you 1 mount path for all the disks which are available in each instance. Now, option 2. Now, you can also use Amazon EBS for shuffle storage with the EBS CSI controller, which creates persistent volume claims, which means if you ask for 10 executors, every executor needs 40 GB, it will create 10 EBS disks with 40 GB each. As you see on the slide, every executor has a dedicated EBS volume. But this option gives you to choose from all the EC2 instances that are available today that EC2 offers today. Compared to the previous option that we looked at, NVMe SSD, you only have a limited instances with the D type. But when you wanted to grow the larger cluster and performance is not a concern, then option 2, where you can use EBS CSI controller with the PVCs to run the workloads. And some of the 2 key features that this offers is reusing persistent volume claims. As you see here, on worker node 1 has 2 EBS volumes attached by 2 executors. If worker node 1 gets interrupted by the spot interruption and the node terminates, you can still reuse those 2 volumes for when the new node comes up. So with this feature, when the new node comes up, it attaches to the existing EBS volumes rather than creating a new EBS volumes, which means it can start the process where it is stopped rather than redoing computing from the scratch. And further to this, you can also leverage dynamic resource allocation, which what Spark offers, which helps you to scale dynamically based on the task load. Now, moving on to compute, I think this is one of the common asks that customers ask about. When you want to run Spark on Kubernetes, on EKS, one thing to remember, Spark driver is a single point of failure. So if the driver gets killed, the entire job gets deleted. So you have to restart the job and restart the computing process. So to avoid that situation, we highly recommend you to run Spark driver on on-demand instances only. If that is not cost-effective for you, we recommend you to look at reserved instances, which is 72% off, up to 72% off from on-demand instances specific to the Spark driver. For Spark executor parts, you can use Spot instances with the help of Carpenter or autoscalers. You can scale up and down. And if the executor parts even gets deleted or the nodes are interrupted by the Spot, and driver can still spin up those executors on the new node and continue the process. And when it's come to compute, Som already explained, the Pinterest they started the journey on Intel, but then eventually moved to the Graviton, and they have seen a better performance and reduced costs. So we highly recommend you to look at Graviton 3, and which we have tested. It works really well on Spark running on EKS. Now, how many of you have hit the out-of-memory error when running Spark on EKS? Right? I think I see a lot of hands here, and I tend to get this question quite a lot from a lot of the customers asking, because most of you are moving your workload from Hadoop to EKS. When you're moving from Hadoop to EKS, the one thing that you need to consider is the memory overhead factor. So by default, Apache Spark has 0.1%, which is a 10% of memory, which is used as the memory overhead factor. But that is OK for running Scala jobs or Java jobs. But when you want to run PySpark jobs on Kubernetes, one thing to consider, you need to give at least 40% of memory as a memory overhead factor to run PySpark job on Kubernetes cluster. Now, moving on to the auto-scaling bit. I see customers using mix of both options, using static clusters like Pinterest do, where you can use reserved instances to run your Spark on EKS workloads. And at the same time, a lot of customers who wanted to optimize for the cost, they want to leverage cluster autoscaler or a Carpenter. And I highly recommend using Carpenter, which is more powerful, and it's an operator-based solution, does not require managed node groups or cluster autoscaler. All that you need, operator installed on an EKS cluster. Once that is installed, with the template that you see here, that's a node pool template we used to call as provisioners in the previous version. And with version 0.32, it's called as node pool. Just define one node pool as a simple YAML manifest. And within the node pool, you can define the instances, Spot and on-demand. And then when you run your Spark jobs, you have a concept called pod templates for both the drivers and executors. And within the pod templates, you can define that you want to run driver on an on-demand instance, executors on Spot instance, using Carpenter managed labels. So with Carpenter, we'll spin up those nodes for you. And once the job is finished, and the Carpenter will scale down those nodes for you automatically. And the speed of the Carpenter compared to cluster autoscaler, a Carpenter at the moment, it can spin up the node under a minute, compared to cluster autoscaler can take up to 2 to 3 minutes. Now, so there's a question that customer asks about, hey, with the cluster autoscaler, we use a lot of launch templates, and we do a lot of configuration with the user data, and so on. Can we do the same thing with the Carpenter? Yes, you can, with the help of EC2 node class. This is another template. So you can use the EC2 node class, and you can define your user data with the EKS optimized AMI, and then configure the way you want it to, which is going to create a launch template for you behind the scenes and spin up a node for you. And you can even use custom AMIs. And as you see here, we also mentioned about configuring RAID 0. So when you want to spin up, when you want to leverage NVMe SSD instances and with the Carpenter, you can choose a range of instances, C5x large to C524x large. So with this configuration that you see on the slide, which identifies whether there are any NVMe SSD instances available in the EC2 instance, if it does, then it formats and mounts that disk to your EC2 instance, which makes it available for the data engineers just to use one path as a shuffle data storage. Now, moving on to Kubernetes batch schedulers. So with the Kubernetes, it comes with the default batch scheduler. It's a single queue, and when you run hundreds of jobs, it goes into the queue. It's a FIFO queue, and it takes one job at a time and plays those workloads. But when it comes to the customers who come from Hadoop workloads and the likes of using Yarn, and they wanted to see multiple queues so that multiple queues can be used when you want to run your Spark jobs on EKS as well. So to fill that gap, there are batch schedulers that evolved. One of them is Apache Unicorn that Pinterest mentioned that they are using, and there's another tool as a Volcano, which is mainly used for one of the key features. What this offers is a multi-tenancy and resource isolation. Say, for example, you have multiple teams within your organization, and you want to control how much CPU and memory they wanted to use. With these batch schedulers, you can create multiple queues, and you can set the quotas for what each queue can use it. So that way, we can avoid the noisy neighbor situation, and the multiple teams can access what they have been given in the first point. And it also provides various workload queuing. You can use phase scheduling or FIFO queues. And most importantly, the gang scheduling. This is a key feature what these batch schedulers offers. Like I talked about before, when you run a Spark job, it's a two-step process. The first thing, the driver gets created by the scheduler, and the driver requests for the executors. And then scheduler will schedule those executors. As you see, that's a two-step process. To avoid that, the gang scheduling, in this case, when you submit 10 jobs, and gang scheduling will create a temporary pods for the driver and the executors, and it deploys as an application rather than scheduling as pod by pod, which is a really cool feature. That's something you should look into. And in addition to that, you have application sorting, job priority, and preemption features. There are various other features that these batch schedulers offer, and I highly recommend using these batch schedulers when you're running Spark on EKS. Now, moving on to metrics, right? So we are running Spark on EKS now. How do we actually monitor my Spark jobs on Kubernetes? That's a big question, right? So with the open source ecosystem, the CNCF ecosystem that offers with the Kubernetes, you have a number of tools that you can use, including the vendor solutions as well. But in this solution that you see, we are using Prometheus, which is used to store the metrics, and then writing those Prometheus metrics using remote write method to Amazon Managed Service Prometheus. And then you can use Grafana to visualize those metrics. There are some open source dashboards out there which you can use Apache Spark for the Grafana dashboards to visualize the metrics, which is not only the node resource utilization, but also your JVM metrics for the Spark job to look at the granular level, how your shuffle data is performing, and how each task is performing. You can go into that granular level. But one thing to notice here, Apache Spark added this Prometheus servlet. It's a class within Apache Spark, which allows you, it's a default configuration. Within the Spark configuration, when you're running a job, you can define saying, I want to write these metrics to Prometheus. It's a built-in feature that comes with Apache Spark, which exposes these driver and executor metrics to Prometheus, and Prometheus extracts those metrics, and then you can use it to visualize using Grafana. In addition to that, you can also use CloudWatch Insights, and you can also use the CloudWatch dashboards. Now, most importantly, Spark History Server, which is a very important tool for all the data engineers who wanted to tune their data processing jobs to see how it is, how bad, how good the code is written. In some situations where you can see some of the stages takes a longer time. The one way to identify is looking at the Spark history server to visualize which stage is taking time so that you can go back and optimize your code to make it perform better. And everyone wants to visualize, all the data engineers, while the job is running. So with tools like Spark Operator, which provides inbuilt feature where you can create an ingress object to visualize Spark Live UI while the job is running. So with the options that we have within our blueprints, you can enable the event logs to write to an S3 bucket, and you can deploy Spark History Server pointing to the S3 bucket and visualize the both historical metrics as well as live metrics using ingress and the load balancer. Now, Spark logging. Now, we talked about the metrics. Now, coming back to the logging. With Hadoop, it does all the aggregation. How does logging works on Kubernetes specific to this? You need daemon sets like FluentBit to extract these logs from all the Spark pods, driver and even the executors. In this example that you see, I have 2 drivers running, and then I have a FluentBit pod that's running within the same node. The FluentBit is a daemon set. It extracts all the logs from every single pod, both the drivers and executors, and you can configure to write to an S3 bucket or to other destinations that FluentBit offers. So it is more cost optimized when you write to an S3 bucket, and you can use Athena or various other tools to query these logs and to see what's going on with the job. And the most important best practice when it comes to scalability of running these workloads on EKS is a lot of these daemon sets sometimes makes too many calls to the API server. One thing to consider if you bring any open source tool into EKS, identify how that operator or a daemon set is performing in terms of making calls. Is it making too many calls? In such cases like in FluentBit, we recommend using extra filters where it basically says, if you notice in there, I said use kubelet is to true, which means if FluentBit requires any metadata, it can get from the kube within the node itself rather than making a number of calls to API server, which is highly recommended when you're deploying FluentBit, which reduces the number of calls that you make and increases the performance of your scalability of your jobs. Right, with that, I'm going to hand over to Alex. Thank you.
Awesome. Thanks, Vara. So tons of great information, wonderful story from Soam and Pinterest, and a lot of great learnings from Vara. So how can you go home and get started with this? Well, we highly recommend that anyone getting started, even if you already are using this today, that you use our data on EKS blueprints. You can see a screenshot of those on the right, one of those reference architectures, and the sample code down at the bottom right. You can use these blueprints, again, to build the resources and all the things that you need to run these workloads in your environment and use this sample code to test. The majority of our blueprints are built in Terraform, but even if you don't use Terraform or if you already have these running in your environment, we highly recommend that you use our blueprints for the best practices. All of those learnings that Vara has gleaned from working with customers and that he presented today, all of those are already built into these blueprints. So even if you can't use them as is and deploy them into your environments, there's still a lot of learnings that you can gather from reviewing those. So we highly recommend starting with the blueprints. And beyond that, you can engage with us on GitHub. There's a QR code on the screen that's to our GitHub issues. If you have questions or if there are patterns that you don't yet see on our website that you would like to see, or anything that you would like to share with us, we highly recommend that you would ask that you engage with us there. And with that, that's all that we have for you today. We have about 10 minutes left and would love to take any questions that the group has.